From your previous study of oscillators, you've learned that frequency stability is of the utmost importance. You might ask, why all of the concern about frequency stability? As an example, let's consider a radio broadcast station. I have here a book of FCC regulations governing the operation of radio broadcast stations. One particular regulation prohibits the frequency of the station from changing more than a few cycles, and it's a pretty stiff regulation. But it must be so that the station will not interfere with another station operating on a nearby frequency. Now, for this reason, the oscillator producing this frequency must be one with the very best frequency stability. An oscillator capable of producing such an output is the crystal-controlled oscillator. We're not going to study the oscillator circuit in this lesson, but we will study the characteristics of the crystals used in such a circuit. And here I might add that the crystal will be used as the frequency determining device of the oscillator, in much the same manner as a coil and capacitor was used in oscillator circuits previously covered. Now, some of the items that we're going to discuss are the use of crystals, types of crystal substances used, crystal cutting, types of crystal cuts, crystal characteristics. We'll see the purpose of a crystal holder, the frequency stability of crystals, and a little bit later we'll discuss overtone crystals. Now, there are many types of crystal substances, but not all are suitable for use in oscillator circuits. A crystal used in oscillator circuits must possess a characteristic known as piëzo-electricity or the piezoelectric effect. Let's look at a definition of the piezoelectric effect. Now, the piezoelectric effect is defined as the property of a crystal by which mechanical stress produces electric charges, and conversely, electric charges produce mechanical stresses. Now, at this time, you should complete item 1 of your TVI guide. Now, this is saying nothing more than if a voltage is applied to the crystal, it will vibrate. The amplitude of these vibrations are much greater at one frequency than at any other frequency. Now, this one particular frequency is called the natural resonant frequency of the crystal. Now, let's look at some of the crystal substances that possess the piezoelectric characteristics. They are Rochelle salt, tourmaline, and quartz. Now, we should include these substances in item 2 of the TVI guide, the A part of item 2. Now, of these three, Rochelle salts exhibits the piezoelectric effect to the greatest degree. However, quartz crystal is most generally used because it has a greater mechanical strength. Now, at this time, let's complete the B part of item 2. The substance most often used in oscillators is, go ahead and complete that blank. It is quartz crystal. Remember, it has a greater mechanical strength. Now, I want to show you a piece of quartz crystal in its natural form. Now, if we were to examine this carefully, we can see that the quartz crystal has a hexagonal cross-section. That is to say, it has 6 sides. Now also, quartz crystal in its natural form has pointed ends. This one doesn't because a primary cut has already been made on this crystal. Now let's take a look at this drawing so that we can determine more about the quartz crystal. There are two views. The top view indeed shows us that the quartz crystal has a hexagon shape, 6 sides, while the lower view points out that indeed the quartz crystal in its natural form does have pointed ends. Now, quartz crystal in its natural form cannot possibly be used in oscillator circuits. It must be cut in a specific manner to exhibit its piezoelectric properties. I know all of you at one time or another have heard of diamond cutting. The reason a diamond is cut is to give it brilliance, and the manner in which it's cut will determine its degree of brilliance. Now, a piece of diamond in its natural form would never be used in a diamond ring, just as a piece of quartz crystal would never be used in an oscillator circuit. Now, when a piece of crystal is going to be cut, imaginary lines are used as the reference points for cutting. And these imaginary lines are known as crystal axes. Let's take a look at this drawing of a crystal and see the exact location of the crystal axis. The axis passing from point to point, or end to end, and directly through the crystal is known as the z-axis. Remember, from end to end, directly through the center. The axis passing through the corners of the crystals is known as the x-axis. Remember, it goes through the corners. While the axis perpendicular to the faces of the crystal is known as the y-axis, going through the faces. Now let's remember these are only imaginary lines and are used as reference points when cutting the crystal. Then at this time, complete item 3 in your TVI guide by labeling the axes there. Now, all crystals are not cut in exactly the same manner, just as all diamonds are not cut exactly the same. The properties which a crystal exhibits are dependent on the manner in which it's cut. Now, there are many different cuts, but we're only going to examine 3 basic cuts. Let's go to this chart and see exactly how we make these 3 particular cuts. The first cut is made perpendicular to the x-axis, which you will recall passed through the corners of the crystal, perpendicular to that axis and parallel to the z-axis. Now, to get a more realistic view of this cut, let's go to a mock-up. Remember, we're considering the x-axis passing through the corners of the crystal. The cut is made perpendicular to this x-axis and parallel to the z-axis. And the cut would look something like this. You can see that it's only a small portion of the natural crystal. Now, since this cut was made in reference to the x-axis, it is known as an x-cut crystal. Okay, let's go back to the chart and see how another cut is made. For this cut, we will use the y-axis, which passed through the face of the crystal. This cut will be taken perpendicular to the y-axis, and it also is parallel to the z, which you will recall ran through the center of the crystal. Remember, perpendicular to the y, parallel to the z. And again, to get a more realistic view of this cut, let's go back to the mock-up. Remember, the y-axis passed through the face of the crystals in this manner. We'll cut perpendicular to that and parallel to the z-axis. And we come up with our second cut, which in this case, since we took it in reference to the y-axis, would be known as a y-cut crystal. Then let's go back to our chart for the third and final cut. Now, this time we're going to cut at an angle from the z-axis. Recall the z-axis passes through the center of the crystal from end to end. And for this cut, we'll cut at a 35-degree angle from the z-axis. Remember, 35 degrees from this z-axis. Okay, back to the mock-up once more. Now, in this case, the crystal cut is taken right in, or made right into the face of the crystal. Remember, the z-axis is running down through the crystal in this manner. And we'll cut at a 35-degree angle from this z-axis. And removing the cut from the crystal, again, only a small portion of the natural crystal, we call this cut an AT cut. An AT cut crystal. Okay, let's go back to our chart once more, and I want you to complete item 4 in the TVI guide. Now, we've seen from the mock-up what these three cuts look like. Let's go over, and I want to show you the actual cuts now. I have here 3 crystal cuts. Now, as you can see, they look like small, thin wafers, and each cut looks very similar. Each cut looks very similar. Now, all crystals look the same, but not all will exhibit the same characteristics. Now, you'll recall earlier we mentioned the resonant frequency of the crystal. Not all crystals, naturally, will have the same resonant frequency. Its frequency will be dependent upon its thickness. Let's take a look at 2 pieces of crystal cuts and compare this difference in thicknesses. As you can see, the thinner cut here, the thicker cut here. We're indicating here that the vibration of this thinner cut, or the frequency, is greater than this cut. Now, this will always hold true. The thinner the crystal cut, the higher the frequency of oscillation. Okay, then at this time, let's refer to item 5 in our TVI guide. You read along with me and then complete that statement. In order to increase the frequency of a crystal, it should be cut, we just saw that, it should be cut thinner. Now, another characteristic which will be different for the various crystal cuts is the temperature coefficient of the crystal. The temperature coefficient. Now, this is a new term, so let's define it. Temperature coefficient is the relationship between temperature and frequency change. Then at this time, complete item 6 in your TVI guide. Temperature coefficient is actually the effect that a change in temperature will have on the frequency of the crystal. Now, let's compare the temperature coefficients of the 3 cuts that we just considered, the X, Y, and AT cut crystals. To do that, we'll use this chart. On the left, we're indicating the type of crystal cut, the X, Y, and AT. Let's begin then with the X cut. The temperature coefficient of the X cut is negative. This means that if temperature about the crystal increases, the crystal frequency will decrease, a negative temperature coefficient. An increase in temperature, a decrease in frequency. The Y-cut crystal has a positive temperature coefficient. If temperature increases, the frequency increases also, a positive temperature coefficient. The AT-cut crystal has a 0 temperature coefficient. That is to say, as long as the temperature ranges between 40 to 50 degrees centigrade. Remember, as long as the temperature is within this range, the frequency of oscillation will remain the same. Then the AT-cut has a 0 temperature coefficient. Now, at this time, you should complete the chart in item 7 of your TVI guide. Now, from this, you should be able to reason that the AT-cut crystal would be extensively used. Now, there are a few other crystal cuts with better frequency stability, but these will not be discussed in this lesson. Now, when an extremely high degree of frequency stability must be maintained, the crystal will be placed in a temperature oven. A temperature oven. A temperature oven is nothing more than a thermostatically controlled container used to maintain the crystal temperature in its proper range. And in doing so, of course, we have a high degree of frequency stability. Then let's go to item 8 in our TVI guide. When a high degree of frequency stability is to be maintained, a crystal will be placed in a temperature oven. Temperature oven. Nothing more than a thermostatically controlled container. Now, in order for a crystal to be used in an oscillator circuit, it first must be placed in a holder. Now, the crystal holder will support the crystal physically and provide the electrodes by which this voltage is applied to the electrode. The holder must allow the crystal maximum freedom of vibration at all times. Let's look at this drawing of a typical holder. The crystal will be placed in the holder between two parallel plates. The plates have an air gap between them, which allows room for the crystal to vibrate. The two plates then are connected to the pins. Now, these are the pins that will allow the voltage to be applied to the plate. And also, the pins will allow the crystal to be connected into a circuit in much the same manner as a vacuum tube. The spring will keep a constant pressure on the plates and hold them firmly in place. The crystal holder cover usually indicates the fundamental frequency for which this particular crystal was cut. In this case, the crystal was cut to oscillate at a fundamental frequency of 430 kilocycles. Now, so far we've seen the physical characteristics of the crystals. Let's now see how the crystal reacts electrically. To do this, we'll look at the electrical equivalent of a crystal and its holder. The crystal itself, when vibrating, acts very similar to a series resonance circuit. containing resistance, inductance, and capacitance. Remember, this is when the crystal is vibrating. Now, when the crystal is placed in the holder, the capacitance of the holder will be placed in parallel like this. CH, the capacitance of the holder. So this capacitance represents the holder capacitance. This represents the vibrating crystal. Now, at this time, you should complete item 9 of your TVI guide. Now, just because this vibrating crystal is equivalent to, or is the equivalent of a series LC tank circuit, I don't want you to think that it's the same thing, because the crystal will be far superior to the LC tank circuit. Now, the Q of the crystal circuit is many times greater than that of the LC circuit. Let's take a look at the comparison between the Q of a crystal and an ordinary LC tank circuit. The Q of an LC tank circuit is seldom greater than 2,000, whereas the Q of the crystal is sometimes as great as 30,000. And as comparing these two, you can see that the Q of the crystal would be many times greater than that of the LC tank circuit. Now, because of the high Q, this would mean that the crystal would have better frequency stability, because its bandwidth is much more narrow than that of the LC tank circuit. Then at this time, let's complete item 10 in our TVI guide. The Q of a crystal is than that of an LC tank circuit. Go ahead and complete that statement. Now, let's look at some of the values, both physical and electrical, of a typical crystal. Physical size, a typical crystal would have a thickness of about 0.025 inches. The width would be about 1.3 inches. The length would be 1.08 inches. And with these physical characteristics, the resonant frequency, or the fundamental frequency, would be 430 kilocycles. Now, with this physical dimensions, or these physical dimensions, let's look at the electrical values. The vibrating crystal would have an inductance of about 3.3 Henry. A capacitance of 0.042 microfarads. The capacitance of the crystal holder would be about 5.8 microfarads. And this crystal would have a Q of around 23,000. Now let's remember, these values were for a crystal cut for a fundamental frequency of 430 kilocycles, and will not hold true for all crystals, but it does give us an idea of relative values. Since the crystal is going to be used in an oscillator circuit as the frequency determining device, it must be represented on the schematic diagram. Let's take a look then at the schematic symbol for our crystal. These two plates represent the crystal holder, while this area would represent the crystal itself. Now, this is the schematic symbol of a crystal used in oscillator circuits. So while looking at this, complete item 11 in your TVI guide. Earlier in the lesson, we discussed the various crystal cuts and how each was different from the other. However, they do have one thing in common. That is, they can be made to oscillate at frequencies other than that frequency for which they were cut. Now, when a crystal is used in a circuit in this manner, it's referred to as an overtone crystal. An overtone crystal. Now, getting a crystal to act as an overtone crystal is nothing more than causing it to oscillate at a harmonic of the frequency for which it was cut. And I might add here that the crystals will oscillate only at odd harmonics of their fundamental frequency. Now, for example, if a crystal was cut for a frequency of 10 megacycles, it can be made to oscillate at 30 megacycles, the third harmonic or the third overtone. You might ask, how is this accomplished? Simply by increasing the feedback to a point where the crystal is shocked into vibrations at the odd harmonic rather than the fundamental frequency. And let's determine what's happening when this is true. Now, here we're indicating the distortions that exist in the crystal when it's oscillating at its fundamental frequency. Here is representing the crystal at rest, no oscillation. Here the crystal is deformed to produce one alternation, and here it's deformed in the opposite manner to produce the other alternation. Now, this is when it's oscillating at its fundamental frequency. Notice that the deformities are opposite for each alternation. Now, here we're representing the crystal when it's made to oscillate in the third overtone. Now, let's notice that the crystal breaks up into 3 layers when it's oscillating at the third overtone. Now, this is representing the deformed layers to produce one alternation. Here, the deformed layers for the other alternation. And let's notice that the deformities are opposite for each alternation. Now, if the crystal is made to operate on the 5th overtone, it breaks down into 5 layers. If it's made to operate in the 7th, it breaks down into 7 layers and so on. But I might hasten to add that a crystal cut for a fundamental frequency is limited to only a few overtones. When higher overtone modes are desired, then a crystal is precision ground and mounted in a special holder, and it would be used specifically for these higher overtones. Then let's stop for just a moment and complete item 12 in our TVI guide. A crystal which is specially cut and ground to oscillate at more than one frequency is called an overtone crystal. An overtone crystal. Now, let's recap a few of the points that we've discussed in this lesson. First, we saw the use of the crystal. Now, we said that the crystal must exhibit the piëzo-electric effect. And we define the piëzo-electric effect as the property of a crystal by which mechanical stress produces electric charges, and conversely by which electric charges produce mechanical stresses. Then we saw the 3 substances used: Rochelle salts, tourmaline, and quartz. We said that Rochelle salts exhibit the piezoelectric effect to the greatest degree, but that quartz is most generally used because of its mechanical strength. Then we saw the 3 basic crystal cuts that we were considering: the X cut, which is made perpendicular to the X-axis, the Y cut, which is made perpendicular to the Y-axis, and the AT cut, which is made at a 35-degree angle from the Z-axis. And then we define temperature coefficient as the relationship between a temperature change and a frequency change. And then we gave you the schematic symbol for a crystal. This represented the crystal holder, this the crystal itself. Now, in concluding, we can say that the one big advantage of the crystal is its frequency stability. Remember, it has a very high Q, giving us a very narrow bandwidth. Then we have one more TVI guide guide item to complete. Item 13. The main asset of a crystal oscillator is its frequency stability. Frequency stability. That just about concludes the lesson on the characteristics of crystals. So until another time, so long.
Do